Good evening. Welcome to the 27th Emeriti lecture, sponsored by the UCSC Emeriti Association and by the Chancellor's Office, who provides the goodies afterwards and also the expenses of videotaping this for posterity. This series was started by Joe Burnett, who thought it was important to convey to the public and to our colleagues the important research being done by Emeriti after retirement without pay. And in fact, the amount of teaching, research, and grant funds raised by Emeriti has been called the 11th campus of the UC system. So it's interesting that the work continues. And we're privileged tonight to hear an excellent lecture. And I'd like to refer to 2 years ago, we also heard an Earth Sciences lecture by Professor Emeritus Jim Gill. And I thought, what a cool idea to have an earth scientist introduce an earth scientist. And so I called Jim and he agreed, and I was thrilled because he can do an excellent job. So Jim, I'd like you to introduce our speaker tonight.
Well, it is a pleasure to introduce my friend and colleague Rob Coe to talk about something that he knows more about and has contributed more to than probably anybody on Earth. So his talk will be authoritative as well as informative. Rob was the first faculty member of our department after its founder, Aaron Waters, who was a geologist. It was then called the Earth Sciences Board, not the Geology Department. And that says a lot about Aaron and Rob and UCSC. Rob's undergraduate degree from Harvard was in physics. His PhD from Berkeley was in geophysics, experimental rock magnetism. And his postdoc at the Australian National University was also in geophysics, but a different area, experimental rock deformation, kind of materials science, phase transitions and silicates. And Rob started teaching here in the spring of 1967, 50 years ago, as a young geophysicist amongst geologists who were friends of Aaron's and twice his age. His entire career has been here at Santa Cruz. He's been department chair, served on Senate committees, done extensive professional service. And for several years at the beginning, he was a resident preceptor in Crown College, where he met his wife, Signet. He became a distinguished professor in 2004 and an emeritus one in 2012. He's won many honors along the way, a Sloan, a Guggenheim, Fulbright, von Humboldt fellowships. He's a fellow of the American Geophysical Union, an honor limited to 0.1% of its membership. And last year he received that organization's Fleming Medal that for more than 50 years has been given to all of the top people in his field. His publications have been cited thousands of times, more than 30 of them cited more than 100 times each. And in our world, that's a bit like being on the New York Times bestseller list for years. Rob has studied reversals of the Earth's magnetic field throughout his career by finding rocks that formed during field reversals and measuring their magnetic properties. And he'll share some of that with us tonight. But in addition, he's used rock magnetism to study the tectonic history of the rocks themselves, where they came from, when and how they wound up where they are now. And those interests have taken him and his rock drill to many remote parts of the world, especially Western North America, China, Central Asia. He's lived and worked extensively in France and Germany, and here at home, he created that building on the top left that exactly cancels the Earth's magnetic field in Santa Cruz, and that houses diverse custom-built, or at least modified, equipment that's needed to make the measurements that he'll talk about tonight. You may also be interested to know that Rob first visited China in 1971. When Kissinger was there to arrange Nixon's visit the following year. You can't say that sentence about many people. And you may want to celebrate that by coming to hear the local Santa Cruz Symphony perform the Chairman's Dances from John Adams' opera Nixon in China 2 weekends from now, November 18 and 19, in concerts that also featured Leonard Bernstein and Beethoven's Seventh. And I close with one personal anecdote. Soon after I came to UCSC, I wound up talking to one of Rob's grad school classmates from Berkeley, who was by then an accomplished professor at MIT. He asked how Rob was doing here, and when I said he seemed to be flourishing, the fellow said something like, well, you know, at Berkeley, we all knew that Rob was the brightest of the PhD candidates amongst us and was destined for scientific greatness. So none of us could figure out why he went to Santa Cruz. And we thought he wouldn't stay long. Well, to our good fortune, Rob embraced the quirkiness of early UCSC. He thrived, he stayed, and he's our longest strand of departmental DNA. So we're fortunate to learn from him tonight. Rob, thank you for all you've done for UCSC.
Can you hear me all right? Well, a lot of what Jim said is true. This is the only job I've ever had. The only real job. And even without knowing what Jim was going to say, I was going to start by some thanks. Thanking the Emeriti Association for inviting me to speak, and to Jim for his wonderful introduction. And then I wanted to also go on and thank UCSC for the opportunity to help start our department, to teach and build a lab and pursue my research for, it's been a long time, 50 years. And finally, to the students, colleagues, and technical and administrative staff, and also to give special thanks to a few people who have been instrumental in this particular topic of research. These are Walter Schillinger. Let's see if I can make this work. Walter Schillinger here and Eli Morris, technical people. Nick Jarbo is a graduate student who had a lot to do with the work that we're going to do here, but also special thanks to Michel Prévost, long-term French colleague, Joe Littacote, one of our first grad students here, Shishi Zhao, who's way back there in the shielded room, and Gary Glatzmeyer, whom some of you know, but he's retired up to Oregon with his alpacas. There was something else I was going to say, but it's escaped me. Well, I thought I would start with a bang. I can't see way back there, so I don't know what the audience comprises. But I thought since this was supposed to be a public lecture, I should put in some things that ordinarily I don't know how to use. So in 2003, there was this Hollywood film called The Core, and it was a science fiction disaster movie. And it was overblown and loose with the truth. It fits right in. But it did raise public awareness that the Earth's magnetic field does more than affect compasses. And it also had another great virtue, because it's the only movie that I know that the hero is a geophysicist and even a geomagnetist. So, yeah, that's really good. Well, in this movie, at the beginning, the core, motion in the fluid core of the Earth inexplicably stops. They don't get into that. The magnetic field decays away, and it leaves the Earth exposed to the solar wind and to cosmic radiation. And then terrible disasters start to happen. That's a lot of the movie. But our hero's team, he saves the day. They pilot a vessel that gets made in record time that can somehow or other travel through 2,900 kilometers of solid rock in the mantle, all the way down to the core, and into the core. And there, they set off a carefully timed sequence of H-bomb blasts to jar the core back into motion. So we'll see if I can put this in motion. Looks like it's going. So there was the first H-bomb. They're down in the core. Up, there's the last one. I had this set louder before. I liked it when it was louder. Now we're up in NASA headquarters. Yeah, I wish I'd seen it. So the field came back and civilization was saved. But, you know, they made one terrible omission that would have made the movie much better. The field could have come back in reversed polarity instead of normal polarity. I don't know how they missed that. They didn't have me as a consultant. So now to get serious, scholarly, geology is a historical science, and our documents are mainly rocks. It was this fact that actually attracted me into geology, geophysics from chemistry and physics, which I had as an undergraduate. But just like with historical documents, these rock documents, you have to interpret them or sometimes even decipher them. Because just as with human documents, they carry information that may be biased, it may be inaccurately recorded, or it could have been partially or completely rewritten. So here we see two great scientists from the 18th and 19th century in Europe who had a great deal to do with learning how to read the rock, or showing and leading the way how to read the rock record. And what they did was very simple in retrospect. By observing natural processes closely, such as erosion and deposition, and assuming that these processes operated similarly in the past over great lengths of time to produce what they saw, they realized the Earth must be very, very old. So they realized that great chasms and worn-down mountain ranges could be understood in terms of observable rates of erosion extending over great lengths of time, rather than catastrophic events wrought by the hand of God. A minimum age for the age of the Earth of several 100 million years, which is, it's 10 times too young, but it's long, was derived from the thickness of sections of sedimentary rocks arranged in stratigraphic order using the fossil record and superposition. It's not that far wrong for the age of fossils. And then as geologists' sophistication grew, even extreme catastrophic events that are in the rock record, such as giant impacts, they can be interpreted in terms of hugely scaled up events or processes actually observed by humans. Well, the phenomenon I'm going to talk about tonight, it's a bit unusual. That is, reversals in polarity of the Earth's magnetic field, because there weren't any direct observations of the geomagnetic field that people could sensibly use and scale up. The only evidence for field reversals comes from the paleomagnetism of rocks. And our paleomagnetic rock records are lava flows and sediments, so sections of these where you're older at the bottom and younger on top, so that we at least know the direction in which time goes. Now with lava flows, which we sample by drilling usually, here you can see the base of the lava flow here, so it's another one down below. And we don't really have any sensible idea of how much time passed between the emplacement of the lower one and that of the upper. But we do know that they get magnetized at the time they cool. So they give us a snapshot of the field, and actually it's usually very accurate. Sedimentary sections, they offer the possibility of a much more continuous record, although you can be fooled by invisible hiatuses. But their fidelity of magnetic recording is difficult to evaluate, and it's almost never as good as for lavas. So, how long have humankind known about the magnetic field as opposed to just magnets? Well, at least since the Qin dynasty 2,200 years ago in China. Chinese have had one form of a compass or another used for different purposes since that time. But the first magnetic observations that were clearly recorded were started in Europe about 450 years ago. And here we see a record of the rate of change of the direction of the field recorded in Greenwich, England from, oh yeah, that's the wrong one. How many did I go through? There we go. Recorded in the Greenwich Magnetic Observatory between 1600 and 1950. And this direction is expressed in terms of the declination. So that's the angle that the magnetic field differs from north in the horizontal plane, and the inclination, it's the angle that the magnetic field direction dips below the horizontal plane. So you can see here in 400 years, there's been, the direction has changed at about 5 to 10 degrees per century. So we call this sort of change secular variation because it occurs on the human timescale. And it's also accompanied by changes in intensity of the field that we'll see about later. Then the great mathematician in 1840, Gauss, developed instruments to measure the strength of the field. And he also spurred the establishment of magnetic observatories around the globe. So from these ensuing observations that he inspired and promoted, and from the math and from the data that came, and mathematical analyses that he pioneered, we know that almost all the Earth originates inside the Earth. All the magnetic field originates inside the Earth. And by and large, 80 or 90% of the field is that of a dipole at the center of the Earth, tilted a little bit away from the rotation axis as shown in the figure. So those dashed lines are the direction of the dipole field, which are north, and it's a normal field, so they're north and horizontal near the equator, and they're vertical near the poles, vertically down near the North Pole and vertically upwards near the South Pole. But they generally don't coincide with the rotation axis of the Earth, with geographic north and south. And today they're around 10 degrees, it's about tilted about 10 degrees away. Moreover, the average strength of the field, which Gauss pioneered the beginning measurements of it, it's been decreasing steadily since then by about 10%. The remaining 10 to 20% of the field, which is not dipolar, is reasonably called the non-dipolar field. And it is more complex in its geometry, it's multipolar, and it also varies with time in a complex manner. And the overall variability of the field direction then, in intensity and in direction, I already mentioned, we call it secular variation of the field. Well, now we get to the paleomagnetic archive, specifically looking at the question, has the field reversed? Now, humans have known about the magnetic field for a long time, and they've known for centuries that heating and cooling iron in the Earth's field magnetizes it. And since sometime in the 1800s, they've known that this was true for fire and earthenware, for clay pots and things like that. So it's natural to suspect that igneous rocks would carry a magnetization from the time that they originally cooled. Among the scientists who tested this idea was Bernard Broom, and that was in the late 1800s. And he collected oriented samples of relatively young lava flows in the Massif Central in France, and he showed that their magnetizations were close to the direction of today's field, just as he expected they would be. But then he tested this flow here, which is famous. It's called the Oldby flow. And he found that it was magnetized in just about the opposite direction. And moreover, underneath the baked earth that the lava flow had baked was also magnetized in the opposite direction. So, what should we believe? There was a spirited debate, but he claimed that the Earth's magnetic field had reversed direction, and that the whole Earth's magnetic field had reversed direction. And that's kind of a courageous claim based on one lava flow, but he wrote a paper about it, which was promptly ignored for 40 years. And, you can sympathize that people wouldn't think that the whole field had reversed and that you're going to believe that from one lava flow. I was thinking of an analogy with the gravity field. So if we went out to dry lakes in eastern California and saw that some of those rocks that slide around horizontally, some of them had jumped up in the air and come down, which they probably have from earthquakes. But we would be laughed out of the room if on the basis of that we claimed that the whole gravity field of the Earth had reversed. So, so Broom didn't get particular credit for this. Well, so it was forgotten, but after the war, after the Second World War, people started studying paleomagnetism to try to understand continental drift, and they ran into a lot of reversely magnetized rocks. So the whole question came up again. And once again, would you believe this or wouldn't you on the basis of reversely magnetized rocks, that the whole field would reverse? And some ingenious geophysicists actually came up with an idea. Maybe they're self-reversed. Maybe they got magnetized in the opposite direction of the field just because that's the way they work. And he asked a famous scientist, Louis Néel, if he would think about this. And, I don't know, in a couple of years, Louis Néel wrote a paper with 3 or 4 different mechanisms by which magnetic minerals found in rocks could self-reverse. So not to go into them, but that, that made people think a lot. And then in the same year, a Japanese professor and his students, they published a paper that they had discovered a self-reversing rock, and they hadn't even heard of Néel's paper. This was called the Haruna-Dacite, and you could take it and heat it up in a laboratory and cool it down, and it ends up magnetized in the opposite direction of the Earth's field. So one would think, okay, case is closed, right? Probably a lot of people did. But no, the case wasn't closed. And this gets very close to home. 3 Berkeley PhDs of somewhat different ages had teamed together to test the idea of reversals by collecting samples all around the world of lavas and dating them with the new techniques of potassium-argon dating to determine their ages. And the geophysicists, it's 2 geophysicists and a geologist, but both of those geophysicists, they knew a lot of geology, and they knew about the rock record. They knew about they knew that the Earth can do complicated things, and they knew that you need to look for consistency to try to figure out the truth. So they were doing this, and by the mid-60s, they had an unimpeachable case for field reversals. And that's here. Oops, shouldn't give me this tool. That's here in this geomagnetic polarity timescale that, and I think this record came from 1968, which in the column on the right here, the normal rocks are black, and the reversed rocks are in white. The time scale is on the left here. I think it's going from 0 to maybe 5 million years. And these normal and reversed rocks that are shown in these columns here, they come from places really all around the world. So, how would self-reversal, sometimes self-reversal, sometimes not, conspire to produce this this pattern. So this pretty much proved, everyone realized, okay, self-reversal, it happens, but it's very uncommon. And the Earth's field reverses pretty much. In fact, over the last 5 million years, if you figure this out, on average there's a reversal. There's 4 or 5 reversals every million years or so, but they have very different lengths of time. Well, I wanted to go back actually and say something else here. Well, maybe I didn't say it here. But it raises the question of what happens during a reversal. And what I was going to say was, those of us who were just starting our careers around the time this was proved, the natural thing to do was to then go and try to study, well, what happens when the field is actually reversing at these, they're too thin to show here, at the boundaries between reverse and normal. What happens to the field as it reverses? And there were 2 end-member simple models that suggested themselves. Maybe the dipole field just turns over in whatever length of time, or maybe it decays to 0 and regenerates in the opposite sense. So a number of us were attracted to go and try to study this question and to learn more about how the field reverses. Well, it's not easy because it happens in the blink of an eye geologically, so it's hard to find records. It's really hard to find lava flow records where enough lavas are extruded right during a reversal, series of snapshots, to get a picture of what the field did. In principle, it'd be a lot better to go and get sedimentary transition records, but understanding how trustworthy they are is often very difficult, as we'll see. So it's quite difficult to capture a reliable account of what happens during a reversal, and it's really challenging the fundamental ability of our rock recorders, our paleomagnetic recorders, to resolve them. Well, we decided, my French colleague and 2 colleagues from the USGS and I decided to try to learn as much as we could about reversals from these superposed lava flows at Steens Mountain, Oregon. It was already known that there was a reversal somewhere recorded in that section from some earlier work. But at the time, we couldn't know what a good record was going to come from there. This stack of lavas that you see there is 950 meters thick, and it's a pile of hundreds of relatively thin lava flows, not big, thick ones in general, like up on the Columbia River Plateau. And it's now known that they span, quote, only about 50,000 years, which is a very remarkable rate for the accumulation of lava flows. For instance, there's been a continuous eruption basically going on the flank of Kilauea in Hawaii for the last 35 years, and it's still going on at Pu'u'o. Maybe many of you have seen that. And its rate of piling up of lava is 6 or 7 times less than what you see there. Now, the current interpretation, so here is Steens Mountain here, is that that pile there that you see is the earliest eruptions of Yellowstone hotspot eruptions, we call them. But anyway, that form the Oregon Plateau basalt. And we know that activity then shifted north. These formed between about 16 and 17 million years. They're hard to date. Then the vents migrated northward and gave rise to the even huger pile of Columbia River basalts, but very thick flows there between about 15 and 16 million years ago. But as it turns out, this Steens record, it's the best lava flow record that's ever been found, even today. Well, realizing that was true as we studied, we went back many different times. It was sort of a good outdoor vacation, although we always gave a sigh of relief when we got off of this cliff over here, and nobody had been hit by a falling rock or anything like that. But we kept going back many times. We studied something like 1,500 samples for this first record I'm going to show you. And we published these results finally in 1985, after many years of work. Well, here's the directional record that we found in this so-called benchmark record. And I've got to explain this plot to you a little bit. It's, first of all, the whole Earth is shown in that plot. So this left-hand boundary here and this right-hand boundary here are the same line of longitude. Then second of all, we transform the directions to what we call virtual geomagnetic poles, which is the direction that a pole would have for the direction of each lava flow if the field were totally 100% dipolar, which we know it isn't, but it's a convenient fiction. And this transformation then allows us to plot transition paths on a map of the world, and they're much easier to work with and think about and compare from one location to the other. So you'll see quite a few of these plots. So that's not the one that I wanted. So down here is reversely magnetized lavas near the South Pole. And then you can see, did I skip forward a whole bunch? Yes, I did, sorry. This is too fast for me. So the field is reversed. Why did I keep doing that? I got to push that one. The field is reversed. It's a reverse to normal transition. You can then see that it moves off to transitional directions with a cluster here. There's a big gap where it jumps up to normal, but that was only temporarily maintained, and it went back to transitional again between normal and reversed. Then there was another big jump back to this same cluster area, a third jump, and finally going stably and for a long time, and staying in stable normal polarity. And the field intensity, you can see it in the reversed and normal parts of this plot. The bottom plot here is from the bottom of the section to the top, so about 600 meters of lavas spanned here. And when it was reversed, the intensity was around this value. When it was normal, it averaged a little higher for this little bit of time afterwards, but both of these are typical of today's stable polarity field. And in between, it was jumpy, but it went down to as low as 10% of the field during ordinary full polarity. It was interesting that it rose back up almost to full polarity values when the field went to this temporary normal direction, which is in the middle of the transition, because then it dropped again and it didn't go back up finally until the field direction moved up here to normal. So what does this tell us about, what did this tell us right away about the reversals? Well, it can't be due simply to a dipole tipping over, a predominantly dipolar field, because in most places on the globe, the field would go up a bit, and the lowest it would drop would be to 1/2 of the full polarity value. So it rules out that hypothesis. So it fits much better the collapse of the dipole field, leaving a very active, non-dipolar, and what we would call multipolar field. I should also mention that, that at these big jumps, we wondered, since we had such a good record, is this due to very rapid motion of the field vector during part of the reversal, this jump to here, this jump back to here, this jump to here? Or did it just represent a much longer than usual hiatus between one flow and the next flow above it? One would estimate that if it wasn't rapid field motion, that would be maybe a few hundred years or maybe even 500 years between those two successive lava flows. And always, those two hypotheses are always a possibility. That's the way lava flow records are. We did see some evidence at the time that made us suggest that it was possible that the field moved very, very extraordinarily rapidly at this time. In a follow-up study that I'll describe in a little while, it led me to abandon that hypothesis. The other question is, this is a very complex transition path compared to how simple you could imagine that it could be just to go smoothly from reverse to normal. It was so complex that it led plenty of scientists, especially ones who hadn't worked in the nitty-gritty with lava flows, to suggest that there was something wrong, and this record was just one of those records that will end up on the scrap heap. So the question is, could its complexity reflect undetected gross artifacts in the paleomagnetic recording? Well, then it was natural then, since there were no other comparable volcanic records around that were nearly as detailed, and they're rare as hen's teeth, that attention should focus on sediments and see if it could answer this question. And at the time, this was in the mid-'80s, there were already plenty of deep-sea cores being taken and studied for their magnetic stratigraphy, so their magnetic polarity history, as part of the deep-sea drilling program. So the other development there was, which somebody was mentioning to me, our, quote, new magnetometer that we got in 1985. That's when superconducting magnetometers were coming online, and the deep-sea drilling ship bought one and had a lab, and it's always had a lab. And they can measure the weaker, more difficult to measure magnetization of sediments compared to lavas. So it should be ideal. We should be able to get perfect records out of them. But it turns out that through most of the oceans, the sedimentation rate is not high enough to have a chance of resolving one of these records very well. And then where you go places like typically near continents, where the sedimentation rate goes way up, there's often a whole lot of organic material in it, and that leads to the dissolution of magnetite, and the magnetic signal goes away. So it's actually taken a long time of looking, decades of looking, as we'll see, for some very good sedimentary reversal records. But at this time, in the mid and late 80s, this was one of the best records around. You can see a sedimentation rate about 4 centimeters per year. And this is the one I meant to point to click. You can see it's a very simple transition path going almost along a circle of latitude. There is some bumping back and forth after the reversal, going along the same circle of longitude. It's interesting. This core came from the central Atlantic right on the equator. Then a little bit later, a little bit higher sedimentation rate sample was sampled in the Atlantic, but up near 45 north. And it also produced a very simple record like this. It did have a little rebound here, but you could just say this was instability at the end of the reversal. And so people who got these records, they said, wait a minute, this is the way we always thought the Earth's field would reverse. It's well behaved. It's going progressively from this is the most recent reversal, 770,000 years ago. If you hear me slip and call it Matsuyama Bruns, that's what it is. And so you can see why there would be this controversy, especially as more and more sedimentary records accumulated that looked like this. Now, true, it's the same reversal record, but they have very different paths that they travel on. But that would be okay. It would mean the field was not a tipping over dipole, but still it could have a very regular zonal progression of the field. It's not impossible. And if it was non-dipolar field, you wouldn't expect the same path at a site here and a site up here. So, the gauntlets were thrown, I guess you could say, although it was a very long duel that went on. So, right around that time, we got very excited because we discovered, right on the walls of Haleakala Crater on Maui, there's a reverse to normal transition as you walk up the trail in the successive lavas on top of each other. So we got permission to sample over there, not on the trail, but over where the old trail was. And we spent a few years sampling the lava flows and studying them there. Didn't know why that record disappeared. But so this is the record that we found. And unfortunately, you can see it's quite sparse. It does consist of longitudinal tracks, if you could call this a track, but this is a huge gap with no evidence in between. And then there's a rebound after the reversal. It goes from reverse to normal. So the two different paths, they span quite a lot of width of longitude. So you could say it was a complex path, but this was, and it's not so nicely controlled as this sedimentary record we just saw on the last slide. But the record was so sparse that it was hard to make a very strong claim about this. So we weren't, I didn't mention, So we spent quite a bit of time on Maui, a nice place to work, going around and trying to find equivalent sections around the caldera and around other places on Maui where we might fill in some of that sparse record with lava flows that were deposited at a time between where those jumps were. And we never found any. But we decided to try the same thing going back to Steens Mountain because even though we already had a pretty good record, the Oregon Plateau is very large and extensive, and so we hoped we might find more records that would help resolve the question of, for instance, the gaps in the Steens record. And this is Nick Jarboe, who is a graduate student who devoted about 4 or 5 years to this project with me, and also with Jonathan Glenn, who was an earlier student and who was at the USGS by then. So we looked at all these different places over a period of a few years, lots of cliffs of lava, and finally we did actually find 2, if I could see better. That's Steens Mountain right there. And we found the same reversal over here at Poker Gym Ridge, about 100 kilometers to the west, and also at Catlow Peak, I think that's that one, about 100 kilometers to the south. And above there is the record that we found. And down here for reference is the earlier 1985 record. This was published in 2012, maybe 11, can't remember. So the black virtual geomagnetic poles, those are the same as the ones in this record, which is shown for reference. And the red and the blue and the purple, they're from those other sections. And what I'd like you to notice is the beautiful way that they agree with parts of the path of the classic Steens record. So you can see the black and the colored dots agree. They do there. They do a little bit here, but there's not many. There's a bunch up here that agree. But where the gaps were in the old record, like from here to here, that's like from here up to here, we don't have that jump anymore. Instead, the field direction moved off like this. Then it came over and messed around in the northern hemisphere for a while. Then it came back here, where if it was going to be like the old Steens record, it would have jumped to here. But instead, there's all these flows that lie in between, so to speak. So instead, the field went down to Australia, the VGPs, back to another normal area. Then finally, after jumping around, partly from this projection up here in normal polarity, it made its way down like this. That appears over here. So running down through the North Pacific, then down through East Asia, down through the Indian Ocean, South Atlantic, finally getting up to here, where that cluster is. We didn't fill in this gap with any. Okay, but this is pretty convincing evidence that the field did not change its direction very rapidly to account for these directional jumps, because now the jumps have gone away, or they've gotten smaller. So, but also, that's perhaps a minor point, really, but it concerned us at the time. Perhaps more important, you can see, oh my God, the more we sample, the more directions we get, the more complex the field is. So it did have this sort of sequence, crudely speaking, very crudely, reverse to transitional to normal to transitional to normal. Now we've added another normal to transitional to normal, and it's got new swings that go down to Australia compared to the old record, and then it's got this one that goes all the way around like this. So it's gotten even more complicated. So we would argue that, well, now the way these records agree from 3 sections far apart on the Oregon Plateau, and one complements the other, this reversal at least is complex. It's got a complex directional path. It's not just a simple blip from one polarity to the other. Well, what about other reversals? Well, we've never found any lava flow record to rival Steen's, but just last January it was, in this article up here by Jim Channel from Florida, he published a paper describing the results from 5 international, what do we call them anyway, deep sea drilling cores, these 5 here, in the North Atlantic. And they had a higher sedimentation rate by a factor of 3 or 4, or maybe even more, from the earlier records that I showed you. This is just one of these records because they really hurt your eyes to look at. So this is one of these cores, 1306, if you can see it up there. I think that's the southernmost site. This is so complicated, but first let me point out that all these different records from this one core, they all spend a lot of time around cluster area 1, cluster area 2, cluster area 3. And there were 2 holes drilled at this same site, and then they split the core into a shipboard and an archive half, and Jim measured U channels, continuous 1 meter long. Is that how long those core segments are? By pulling these cores, or the pieces of cores, through a pass-through magnetometer to measure them continuously. And so they average over about of the sense coil region, which is about 4 centimeters. So a lot of seeing this string of all these points is just because it's like a running average of at least 4, really more, 1 centimeter samples all next to each other. But all of the 5, and all 5 sites were measured in this way, and they all give this sort of messy picture, but where they're all going to these 3 different, all the records are visiting these 3 different places. And the reason I showed this one is that in this one record, this one core, they also sampled discrete 1 centimeter samples back to back along the core and measured them separately in a magnetometer, where you get a much better measurement and you don't have this big averaging. But you can see it visits these same areas, 1, 2, and 3. And also, just blurring your eyes a bit, the record reminds one a lot of the Steen's record, the Steen's volcanic record. It spans a wide range of longitudes, and there are these areas where the directions. Hello, hello. Can you hear me? Oh. I was warned not to do anything bad, but my thing is here. Oh. Hello? Okay. So it looks like a lot like the Steen's record, with cluster places and spanning a lot of longitude. So now I would say, well, for sure, because this is the most recent reversal once again. So those earlier, quote, good records that just went right along lines of longitude, they can't be right in this record right at the same time. In fact, one of the records with the very simple path came from, maybe it was around here. So it's not that far away from where these 5 cores were. So to me, and I think now increasingly to many people, certainly to Jim Channel, who didn't used to believe this way, it looks like at least the last reversal was complex also, and maybe they all are, or maybe they mostly are. We can't really know, but what it does tip us off to is that it's very hard, even trying very hard over years and many different people, to get a really high resolution record of the Earth's field during a reversal from the deep sea sediment cores. All right. Oh yes, so take-home message, higher deposition rate in these cores, less smoothing of the record. So the most recent polarity transition was also very complex. And the corollary is that those other records were drastically smoothed. Okay, well, we're slowly winding our way towards the end. That's really the rock magnetic, paleomagnetic archive. And I've tried to give you a little bit of a feeling of you have to work pretty hard to extract the truth, paleomagnetic truth from these rocks if you're really pushing them to the limit to resolve polarity changes that happen in only a few thousand years. Take only a few thousand years to happen. So I noticed quite a lot of my physics friends in the crowd here. So you're probably saying, well, heck, let's just model it. And then we can have field directions from all over the globe, wherever we want them. and you know, we can be done with this. And here we see Gary Glatzmeyer, who just recently retired from our department, and before he was here, he was in Los Alamos. And over here on the right, Paul Roberts from UCLA, and from England before that. And just by way of background, I wanted to say that it wasn't until about the early 50s that it began to be generally accepted that the Earth's magnetic field must come from some sort of self-sustaining dynamo originating in the core. This was not because we could model it, but because all the other explanations that had been proffered led to contradictions. But it was clear that, you know, the basic minimum requirements for a self-sustaining dynamo, which is a rotating large volume of electrically conductive fluid, plus heat or some other mechanism to drive fluid motions, that the core fills the bill very nicely there, as you saw from the movie. But how to prove that this mechanism actually worked, it came very slowly because the problem is very difficult. It has to be, the equations can only be solved numerically, and they're computationally intensive, to put it mildly. But by the 90s, a lot of progress was made by these two guys and 2 or 3 other teams working around the world. And then in 1995, this pair published a paper of really the first, just in a general way of speaking, the first 3D physically self-consistent sustaining dynamo model. But more exciting for people was that after they ran it for equivalent of a million years or so, that somewhere towards the end of that simulation, it spontaneously reversed. It just did it. Well, that should put people like me out of business, because now we have a model where you could calculate from their model and their simulation what is the direction of the magnetic field at every point on the surface of the Earth, every point in the mantle, even everywhere down in the core where it gets very complicated. And we can do it for all times. But of course there's a catch, and the catch is that these simulations still today in the biggest, fastest computers and computer clusters, you can't get anywhere near the parameter regime that the core has to be operating at, must be. It has very low viscosity. It's got a lot of potential driving force terms. And so we know that the core motion in detail has to be very, very turbulent. And this is too much for the best computers. You just can't get anywhere, let alone run a simulation for long enough to see if it spontaneously reverses. So intelligent scaling is done. Nonetheless, I should say that there's some chance that this might mean something, because we could hope that some of the larger scale features of the magnetic field, even though they're being neglected at the very small scales in the core and in the fluid motions, that they could still give us insight into what really happens with the field in terms of secular variation and reversals, and just the geometry of the stable field. And indeed, there are plenty of simulations out there now that do a pretty good job of mimicking the geometry of today's field in a gross sort of sense, and its secular variation. And even some of them, like Glatzmeyer and Roberts, they give reasonable approximations of what we think some reversals may be like. So for instance, the one for this 1995 paper, here are 3 snapshots from that reversal simulation. The first one on the left, normal polarity, the second transitional in the middle, the third a little bit later after it's become reversed. So a normal to reverse reversal that happened in this simulation. Oh yeah, I should back up a moment and say, just the fact that it happened spontaneously was a very big discovery, because before that, some people speculated, well, something or other jars the Earth and the core to trigger it to reverse. For instance, meteorite impacts. There were a couple papers about that. But here with these simulations, and lots of different simulations, you see they just happen spontaneously. It doesn't take anything to make it happen. And then I wanted to show this sequence of slides. So what are these lines? These are lines of magnetic field force. So their direction gives the direction of the field where each line is. So blue is inward pointing here, and orange is outward pointing. And this tangle of yarn in the center, what do you think that is? That's the core where the field is actually being generated. So it's very complicated where the generation process is going on. But the part of the field that gets out and makes it to the surface of the Earth out about here, you can see this is really dipolar in geometry, with a north dipole end up here and a south dipole end here. Vice versa over here, although You know, the secular variation of the field is going on, so the dipole axis is tipped a different way here than this one. And in between, it's very complex. It's multipolar. So that was the reason for showing this slide. So multipolar transitional field. So this fits in, you know, in broad detail the sort of stuff that we've seen in the paleomagnetic archive. And then just to show from a later simulations that they did with, well, even better simulations with conditions that are more like would obtain in the core, but still far from the conditions that are really down there. And just let's look at the lower record. The top record, you can do everything with these simulations. That's the dipole path through the reversal. But this one down here is what the field looked like in this simulation for a site that was right here where the star is in the northern hemisphere. This one, I don't have any arrows on here, but I seem to remember that this one went from reverse to normal. But you can see, not to belabor the point, that it's quite complex, doesn't look like the Steen's record, but there's no inhomogeneities in the mantle or anything in this record, so it's a very smooth Earth. But even so, all longitudes are spanned by the virtual geomagnetic poles. So we at least get some reinforcement from simulations, but we have to be careful not to believe them too much, because if we found something different in the paleomagnetic archive, then it's up to the simulators to figure out what kind of conditions are going on down there to reproduce that record, not the other way around. So finally then, what about if the magnetic field reverses again? And these kinds of questions that people like to ask, especially people, you know, trying to get some sort of spectacular story for the news or whatever. So what if the magnetic field reverses again? What if? So there's a NOVA video by the name of Magnetic Storm that it's also over-dramatized and is pretty sappy, but it does get people thinking seriously about the magnetic field, and it has some hero geophysicists in it, but it's not a movie. And but it gets you to thinking about where and how the field is generated, how changeable it is, and especially its potential effects on the environment that everybody wants to know about. So in this video, they explain that the field does quite a bit of shielding the Earth from incoming charged particles that are coming from the sun, or even more energetic ones coming from all around in the universe. So well, that's enough said about that. Let's see whether I can make this one start as well as the last one. Yes.
Up next on NOVA, Magnetic Storm.
So this, I think, came out in 2003.
It's 2,000 miles beneath our feet. The Earth's molten core. Here, a vast ocean of liquid iron generates an invisible force. The Earth's magnetic field. It's what makes our compasses point north, but it does a lot more. It helps to keep the Earth a living planet. Our neighbors, Venus and Mars, have only weak magnetic fields, which means they're unprotected from the deadly radiation sweeping through the solar system. The Earth, on the other hand, exists within a vast magnetic cocoon. sheltered us on our journey through space. But now, scientists have made a startling discovery. It seems there's a storm brewing deep within the Earth. A storm that is weakening our vital magnetic shield.
And then I tacked these simulation records on so we could think about what happens during a reversal again. So, yeah, it raises a lot of questions. And it is true that we have quite significant shielding of the Earth from penetrating. It helps stop charged particles penetrating. They penetrate best at the poles where the field is vertical, and they also will penetrate farther and better and have more environmental effects if the field is weak. So this is why people wonder about, well, what will the next reversal bring, et cetera, when the field is weak and when it's multipolar, so that not all of the vertical magnetic field lines are just near the poles where, they just fry the Swedes and the Norwegians, and but not the rest of us. And but during a reversal, we may have the vertical magnetic field right here for a bit. But remember, we've got the atmosphere, so I don't think it's really so bad. Well, first thing that people often ask is, is another reversal going to come? And yeah, this is now an extended polarity time scale, extended mainly from studying the seafloor stripes on the normal and reverse polarity on the seafloor. Goes back 160 million years. There's many, many, many reversals. So it would be quite amazing if the field had just stopped reversing now and it wasn't going to happen. On the other hand, people like to say it's overdue. We're 770,000 years since we had a full reversal of the field. And I mentioned to you that the average for the last tens of millions of years is 4 or 5 times per million years. So, but there's a strong random character to the reversals. And so, yeah, if you're a betting person and somebody says, well, I just got 10 heads in a row, will you give me 5-to-1 odds that the next coin flip is going to be a heads? Well, I would, because it's been 10 times without one. No, but each flip in an ideal world at least has the same probability, 1/2. So just because we haven't had one for a long time doesn't mean that one's around the corner. Well then, what are the likely environmental effects of reversals? Well, yeah, you can put away your compass. And, we know more and more about different animals that you can prove with some not so easy experiments that they do sense the magnetic field, and some of them use it. I remember one of the first ones I read was about the dance of bees and how the honeybees come back to the hive from where they discovered a lot of good flowers, and they perform this dance. And the plane of they dance, fly, I don't know what, in the nest, and the plane of the dance gives the other worker bees the sense of what direction to go and get more honey. And this was proved way back in the 50s by, what was his name, Lorentz? Was that his name? Conrad Lorentz? that he could change the orientation of their dance by changing the magnetic field. So that looked pretty clear. And now we know a lot of, we've got bacteria, we've got lots of different kinds of birds that it's been demonstrated for, dolphins. So animals are confused. Are they going to die out? Well, we don't know of any extinctions happening at reversal boundaries, especially bird extinctions. So they've got other ways of seeing how to get around, and if the compass isn't working, they'll use these other ways. And people have worked on what the other ways are. Pretty surely, with today's grid system, especially in Santa Cruz, we'd have more widespread and frequent electrical grid failures. For instance, in Quebec in 1989, they had one, and that was right when there was a pretty big coronal mass ejection, which sent a bunch of particles straight at the Earth. And even though it doesn't produce very big electric or magnetic fields on the surface of the Earth, over a big loop of wire, that makes a big difference, big distributed set of power lines, and it blew out transformers. I think they were without power for the better part of a day. So when the Earth's magnetic field is reduced, we could expect more of these. I've heard it suggested more frequent lightning strikes. I've never quite understood the mechanism, but I throw it out here. And it is in that first movie, The Core. The lightning's going all over the place. So, more depleted and widespread ozone holes. So how does that happen? You know, ultraviolet rays are not charged, so they're not shielded by the magnetic field of the Earth. But it turns out that atmospheric scientists at least say that when some of these particles, charged particles, do get into the upper atmosphere, they react, they form free radicals with nitrogen and maybe other species. Those free radicals in a sort of catalytic chain, they eat up some of the ozone. So we would have less of the ultraviolet shielding against the ultraviolet by ozone. And so we'd have a somewhat increased risk of skin cancer that if you looked at the NOVA show through there, they make a great, makes it sound really scary, but I suspect it wouldn't be nearly as bad as smoking or a lot of stuff. And then, of course, looking forward to the auroras, which would not be confined to the poles anymore during a multipolar transitional magnetic field state. And besides that, the field would be weaker, and so they would normally reach to lower latitude anyway. Well, a final question then, because maybe some of you have read things in the paper or heard them on the news once in a while. Some of us, but not me, get on and say, well, the Earth's magnetic field is decreasing at quite a rate, 6% per century since 1900. These are not paleomagnetic. These are records from worldwide magnetic observatories, and now from all sorts of satellite data too. So this is the dipole moment of the Earth. You can see that in 1900 it was about 8.3 of whatever units were in here, and now we're down to about 7.7. So this is pretty significant for a global magnetic field. So there have been a surprising number of people who have said that one reason or another, it looks like we're finally headed for a reversal. So is it imminent? Well, again, this is an old slide, but it's still more or less right. All we have to do is look at paleomagnetic information of what the intensity has been doing over a longer time period. So here we have, let's hope I click the right one. This is the present. This is 50,000 years ago. There's a lot of data from in here that shows that the field was high, about 40% higher than today, 1,500 years ago or so. So it's been decreasing in a more complicated way than this, but at a significant rate. It was lower 6,000 years ago or so, then back up. But out here for some tens of thousands of years, we don't have any high field intensities that I know of that have been recorded yet. So we have. And then just looking at data over tens of millions of years, it's looking like the 10, 20, 30 million year average for the field intensity is more around 4.5 or 5 or maybe a little over. So really, we're abnormally high in intensity. So we've got a long way that the field can go down before it gets to transitional levels. So, and also we know that there hasn't been a real reversal since 770,000 years ago. But I should say, just in case some of you have heard, around 40,000 years ago was the so-called Lechamp event, which was a magnetic excursion. I haven't talked about that, but where the field moved off in many localities around the globe where we have data to directions far from the normal polarity, some of them really reversed, and the field intensity went down, but then the field came back. And if you search hard in the science fiction literature, you can find out one story that supposes that at the time of the Lechamp event, when there were still Neanderthals around as well as Cro-Magnon, this Lechamp event somehow led to a bifurcation of universes, and the Cro-Magnons, we were in one of the universes, and the Neanderthals were in the other, and it's a trilogy, and the Neanderthals get quite advanced in some ways, including computing, and somehow or other they open up a wormhole to our universe. Yeah, I can't remember the author though. Look for it. So I would say finally to close that a reversal isn't likely in many thousands of years, and even if this one is it, and it's really coming and it's going down now, even if it increased its rate a lot, it wouldn't get down to reversal levels for a few hundred years, and probably more like 1,000, 1,500 years, and that's not likely. And otherwise, you could say, oh yeah, we're probably safe for some tens of thousands of years. If we still exist when a reversal happens, our civilization will be much less vulnerable if we've gone to local power generation, right? So if we all have our own solar panels or wind farms or this sort of stuff, and we don't have these big current loops produced by shipping the electricity around power lines that stretch forever across the country. The ultraviolet radiation, well, we still have the atmosphere, and it produces at least half of the shielding of the Earth from particles and stuff like that. Somewhere I saw someone say that it's about the differences if you decided to go from here to Denver and live. I don't know if that's accurate, but gives you an idea that it should be manageable, and we can always carry parasols. And then finally, what I said before, Earth and life has survived many, many reversals, and we have not found any examples in the paleontological record where we can say, oh yeah, this species, even if it's just bacteria, you would think, how do they cope if the field reverses? But anyway, they do. So I think that we can relax and enjoy the auroras. Thank you.